Hello, good morning, good afternoon, good evening. Welcome to this session of SNT 3.2 on laboratories, including transportable and field-based facilities. Radionuclide laboratories and also field laboratories are an important part of the verification regime. And I'm very pleased that there's ongoing efforts to improve the capabilities. And we have in this session three high-profile presentations. I also would invite all of you to look at the corresponding poster session. And of course, you're all aware now how the system works. Please post your questions in the chat area, and if time allows, we will pass those questions on to the speakers. With that, I do not want to spend too much time talking myself. That's not why you're here. I will try to keep the timing of the presentations as close as possible to the advertised times. In the end, we may have, if that works out, we may have 5 minutes time, additional time for questions to all three speakers. So please stay around, ask your questions. We will try to get them answered. With that, without much further ado, I'd like to open the floor to our first speaker. It's Michael Fox, and I believe it's a pre-recorded presentation.
Have one, but I'll give it live.
Oh, okay, even
Yep.
better. Thank you.
Thanks. Okay, should be all set now. Thank you everyone for coming. As Klaus said, my name is Michael Fox. I'm going to talk about the long-term verification of radionuclide laboratories, specifically in this instance USL16, looking at the gain and efficiency stability, going through a little bit of what we do and why I think it's important for the radionuclide laboratories. I'm going to start out with just kind of mapping out the path of the radioxenon and seeing kind of where the laboratories fall in and why it's important for the long-term tracking. So initially, we have the xenon comes through, it's released, goes in the atmosphere, and then it goes through atmospheric transport and is detected in the IMS type stations, whether it's the SANA 2, SPOLX, or the next generation systems that are being looked at. Like here is Xenon International looking at Xenon 135, 133M, 133, and 131M. So a variety of different half-lives for those systems. But if there's a sample of interest, they can take that gas and archive it, and that can be sent to the laboratory then for the subsequent measurement. And so this is the part where I'm going to focus on the laboratory processing and measurement. And because they are not operating 24/7 in the field, I think that's where the importance of the long-term stability and gain tracking comes into play. So this system here that I'm going to focus on is USL16. It was certified in 2016. As any of the other laboratories, it has to have the certified personnel, so set number of operators that are trained on the system, trained how to deal with the chain of custody, things like that. So on our team, we have myself as the lead. We also have processing deputy, analysis deputy, and then about 8 people total who support the operations and analysis of the samples. So when we get that archive container, we take that and we attach that to this front port here. So that's where we attach it to the system. And then in this instance, we attach the bottle here, like I show here, and we use electrically controlled valves to process that gas. And so first we start out with pumping that gas through a liquid nitrogen trap. The liquid nitrogen trap is raised up, the xenon is frozen out within that nitrogen trap, and either the carrier gas of helium or nitrogen flows through that trap and is pumped out with a pump. After that, we have essentially pure xenon. We can quantify that xenon here with a pressure sensor. So this sensor has already a known volume in that area. So we know the volume, we measure the pressure, and it's also a binary gas sensor, so we can measure the concentration of the xenon relative to either the helium or nitrogen and know how much stable xenon we have within that volume. And that allows us to then further on make that activity concentration measurement. So then we volumetrically transfer a portion of that gas into the sodium into our beta gamma detector shown here on the right in the schematic, and the residual gas is left over in this region. We don't do a nitrogen push so that we can keep that gas for a secondary measurement if desired. And so we recollect that with another liquid nitrogen trap, and we put it in this tube, take it off the system, and we have that in our hand in our back pocket should it be needed. So I showed the gas goes into that beta gamma detector. This is the detector we're using on our system, where the gas comes in here through this gas line into the plastic scintillating beta cell, where it's measured for the beta that's there, and a light output is read out with the PMTs. And the sodium iodides measure the gamma particle here in blue from the radioxenon. So on the bottom right-hand side here is where we look at the regions of interest, kind of a schematic of what we look for the different isotopes. The beta on the X, the gamma on the Y, with the 7 regions of interest that we use for the analysis. And each of those isotopes has their kind of special region of interest that we use to quantify how many decays that we have from that isotope, and then we can know what our activity was. And then subsequently with the previous measurement of the stable xenon, we can get our activity concentration. This detector is based on early PNNL detector design. There are efforts underway to either implement or develop new detector improvements, whether it's things like a single PMT that you've seen in some of the other presentations, like on Xenon International, or the measurements that have been done there, or the silicon beta cell, which is something we're looking at, but not necessarily on this. So those are kind of other things that are going to have to be factored in, but it's a story for a different day. And then, of course, with all of the parts and hardware, the detector types, model, numbers, manufacturer, everything goes to the PTS so they can have that information to perform any simulations that are needed. So I mentioned that 7 region of interest plot on the previous slide. And so we use that to calibrate the efficiencies for each of the 4 isotopes, whether it's Xenon 135, 133, 133M, or 131M. And with that calibration, we can know what the efficiency is for each of those isotopes and get the gain calibration as well. We can know we then know that this 131M peak lies in that same spot on each measurement relative to the region of interest. So when we get a sample of unknown activity and isotopics, we can compare that to the 4 plots that we have there and quantify what fraction of that activity came from each of the isotopes and how much activity there was overall. But to do that, we need to know that those regions of interest haven't shifted. And so if those have shifted, then it throws off the isotopics and our calculations. So we want to be able to have confidence that those are the same as they were when we made that initial calibration measurement. We do that through performance monitoring. So monitoring trends in the detector, looking at weekly quality control checks using cesium 137. We put that at the detector, measure the beta gamma plot here with the Compton scatter. Then we can take this plot, rotate it to the side, and see where this endpoint of the beta signal is here on the upper right. And then also compare that to the photoelectric peak for the gamma detection on the bottom plot. So monitoring those two values, what that beta endpoint is and the gamma endpoint, we can know if those are consistent. And knowing that rotation, what angle we had to rotate at, we can also then know if that is consistent between the period of time when we calibrate the detector and when we're about to make the measurement. So we do that using software and we track that gain. Is that gain stable over time? Generally, if we're doing gain corrections, it's going to be stable. but we want to know, have we had to make any major changes to that gain? Has it been fluctuating? Is it stable over the course of a single measurement, a week, a month? So that we can track that, because we're not making sample measurements on a daily basis. We want to know that we can go away for the weekend, come back, and still be the same on Monday as it was on Friday. So using that, we do 2 QC measurements as well, before and after our sample measurement, to ensure that we have stability over that period of time. And it also helps us to monitor for any of the additional gain shifts, as I've been mentioning. The other thing that we do is monitor for the stable xenon in 2 ways. First, we do it, which is not shown here, but we do perform weekly stable xenon measurements, where we generate a bottle of 1 cc of xenon, put it through the system, make sure we still measure 1 cc. However, we want to be able to have a kind of complete picture of the stability and efficiency and kind of quality control of the system. And that's also done with the proficiency tests. Those allow us to compare both the activity concentrations and the ratios of the radioxenon isotopes, and make sure that we're tracking that trend. So here you can see on the circled plots are the USL16 results. Just looking at those, it's done well, but want to be able to see how can we dig into those more. Looking at the 131M, want to see, okay, do we have any trends? Same with the Xenon 133. Looks like it might be a little bit down on some points, but how do we look at everything in general? And so for that, we can then look at the long-term trends of those multiple PTEs. As we have more proficiency tests, we get more data, we can have more of a baseline for what the stability of the detector is and of the system as a whole. So they allow us to look for any kind of systematic variation that we might have, as well as it allows us to look at how are there any trends within the laboratory network, not just on one system at one laboratory, but is there anything across the network that we might need to look at? So you can see here on the left-hand side, we have the Xenon 131M plot, where there's good kind of scatter around 1. So we're good there. Looking at the right-hand plot, we have 133. You initially look at it and say, oh, there might be a trend. It's not very statistically significant. And it is skewed by the fact that on the x-axis, these are sample IDs, not necessarily the point in time. And so, like for instance, these 4 right points all occurred at the same point in time. And so there's some variation across those. And so it makes it tough to look at it and say, okay, we have a clear downward trend, because there is some additional fluctuation and the x-axis is not constant. However, we did take that and it lined up with when we needed to do a recalibration of our system. So we went through, updated a calibration, we could reanalyze it in the results and see, oh, there might have been a slight change upward, brought it more in line with a value of 1. So we might have been on that track where there could have been an issue in the future, but we were able to head it off before anything happened. So a few conclusions. So USL16 NGL has been certified for about 5 years, but it's been successfully operating for nearly 10 years. And we're able to use that that length of time and that data to monitor the trend and the performance, and extend that to see what we think it'll be in the future. With that, routine performance monitoring is needed. It's performed both before and after samples, looking for gain shifts. We do perform stable xenon measurements as well to look for the gas processing trends. And then finally, the proficiency tests kind of pull all that together and allow us to look for improved trend monitoring within the system, as well as within the network. And with that, I'd like to say thank you, and I'll take any questions you may have.
Thank you very much. So far, there's no questions from this chat, but also the other speakers, if they have a question, may raise their hand, of course. Otherwise, it looks to me like the system seems quite stable already. Do you think you can improve this further with the new cells, or
It's quite stable. I think with the new cells, like a single PMT, it will add into some of that stability because you're not also gain matching the PMT on each side of the beta cell or the sodium iodides. And so it kind of it lessens that requirement to have that gain calibration between those two. So you're only calibrating the one point as opposed to trying to optimize both of them on a single measurement.
And I guess it's reassuring that the system is so stable. Because
Yeah, it's nice to see when the laboratory isn't operating. It's not like a station in the field where, oh, we can track all these measurements and have a good day by day play by play of what's going on.
Good. Okay, thank you very much.
Thanks.
And obviously, to the audience, if you still think of questions, please post them. At the end, towards the end of the session, we should hopefully be able to ask them. With this, we come to the second presentation by Matthew Goodwin. And the floor is yours.
Great, thank you, Klaus. Can you hear me okay?
Yes.
Great. Okay, hi everyone, my name is Matt Goodwin. I work at AWE in the UK, and I'm based at in the Noble Gas Laboratory, radionuclide laboratory GBL15. Along with my co-authors here, this is a talk on high-resolution laboratory-based beta-gamma coincidence spectrometry, particularly for measurements of radioxenon. So the UK CTBTO radionuclide laboratory, known as GBL15, is certified for particulate and noble gas measurements as part of the international monitoring system. And to deliver the noble gas measurements, we use a Sauna 2 IMS lab system. And this allows us to quantify Xenon 133, 135, 131M, and 133M from remeasurements of IMS samples. We also have a remit to research new detection technologies in order to improve detection sensitivity and accuracy. And as part of this work, we've been using a PIPS box detector, which has been set up and configured for coincidence measurements with multiple high purity germanium detectors in order to evaluate its performance, and as an option for a future operational laboratory system at GBL15. Here we look to determine the optimal detection limits achievable for this type of system. And as I mentioned, this is in collaboration with scientists from University of Surrey and NPL. So a quick overview of the system that we've been testing and making measurements with. So we've used a PIPS box detector, which was developed by CEA and Miriam. And we've set that up in a low background cave with two BEGI 6530 carbon window detectors. We collect all of our data in time-stamped list mode, and we use custom acquisition software for this. The data is processed using C++ and Root, some software developed by Richard Britton, and then we post-process all of the root files using Python. This allows us to generate electron-photon coincidence matrices from all four gain-matched detectors and create a near 4-pi detector geometry in order to maximize our detection efficiency. So an overview of some measurements then. We've procured some spike samples from Siebersdorf Laboratories. The first one contained all four radioisotopes, and we've also had samples containing just the longer-lived 131M. And we inject the gas straight into the PIPS box and quantify how much was transferred by measurements before and after of the gas vial on a separate germanium detector. We perform our acquisition, and as I said, we collect all the data in list mode, and then we determine efficiencies for the system based on these transfers and measurements. And then we can make coincidence projections and generate our energy-gated coincidence spectra, and this allows us to calculate detection limits. So here's an example of a coincidence matrix then. These have been shown before by many others. In this case, we're showing a measurement of Xenon 131M, and you can see here in the X-ray region that we can pull apart at least 3 separate X-rays, and in this case you can see the K-alpha and K-beta, and also the K-alpha minus the germanium escape peak. And then by putting separate photon energy gates on each of these X-rays, we can project out an electron spectrum for each one. So you can see here I've made 3 projections using very small energy gates in the photon axis and generated and projected out the electron spectra for the K-beta, the K-alpha, and the germanium escape. And you can see in each of those, we can see the conversion electron 129 keV of Xenon 131M. We can then take these separate projections and sum them together to make a summed projection for Xenon 131M. And this gives us the most possible counts for 131M, whilst also in theory reducing any interferences from ground state xenon decays. So we then tested this these sum projections to see how much interference there is from the ground state radioisotopes. So we used the measurements of all 4 isotopes to do this, and you can see the coincidence spectrum here. So by taking gates on the K-alpha X-rays for cesium and xenon, you can see how they differ and how having a high energy resolution really helps you pull apart these signals. So on the top, you can see the cesium X-ray gate and how most of the counts there are from the beta continuum from Xenon 133 decaying. And then if we move the gate ever so slightly to take the xenon X-ray from the K-alpha, we can see here that it's the majority of the counts there are from conversion electrons. And taking an estimate of the beta continuum background here, there's around a 20 times drop in the beta continuum counts per keV at around 129 keV. So this really changes the interferences that we use for the NCC method. And in fact, it also highlights just how much electron scattering is taking place in the VIPS box, and these introduce new interference factors for us to account, particularly for scatter from the higher energy electron into the region of the lower energy electron. We can apply this to the K-betas as well, which I've put here, but it's the same story. So by taking the whole region as if we had a low resolution photon spectrometer, such as sodium iodide, we'd get a spectrum that looked something like that on the right, where we have quite a significant beta continuum, and also that we can see the electron peaks. But if we take our selective gates and sum them back together, we can get the cesium gated spectrum at the top or the xenon gated spectrum at the bottom. Of course, we would use the beta gamma coincidence from something like Xenon 133, so we don't really need the top signal, but the bottom right xenon metastable signal is very helpful because it means that there's less interference from Xenon 133 and 135 into the metastable regions, and this is important. So as we know, Xenon 133 is prevalent in the atmosphere due to civil nuclear processes contributing to the global radioxenon background, and high activity Xenon 133 samples are often measured on the IMS. Xenon 131M is an important radionuclide because the 3 isotope ratio plots do not allow for clear discrimination between a nuclear explosion and a civil source in many cases. So on the 4 isotope ratio plot, it's the 133M, 131M ratio that's the most effective way to determine the possible source type. You can see the line in figure 10, it's almost vertical, and it gives us the greatest discrimination between civil and non-civil processes. So by using high resolution spectroscopy, the effect from the interference of 133 on the detection limit of the metastables is reduced. And this is shown in the plot bottom left, figure 9. You can see our current system using low resolution spectroscopy gives us a greatly increasing critical limit of 131M as we increase the activity concentration of 133 in the sample. But by reducing this interference by having these selective gates, we have that effect is greatly reduced. So this raises some interesting questions. Having improved sensitivity of the metastables, in particular 131M, in real environmental samples can enhance our data set during an event of interest. Remeasurement at a laboratory could improve the sensitivity compared to the station for some isotopes. And this isn't something that we've often seen for noble gas laboratories. It tends to be the particulate measurements that can be improved upon in the laboratory. So with delayed remeasurements, perhaps laboratories could detect isotopes that were not detected in the station measurement during a radionuclide event. This also raises some other questions because there's been quite a lot of work from many different people on different types of beta gamma coincidence spectrometry, and some have used low resolution, some have used high resolution, and this goes for both photon and electron detectors. And here, this work is obviously high resolution in both axes, and our current system is low resolution in both axes, but of course much higher detection efficiency. Others have done some work in low resolution photon spectrometers, but with high resolution electron spectrometers. But what's really interesting, I think, is the top left here. If you had high resolution photon spectroscopy with lower resolution yet higher detection efficiency electron spectrometer. So our working hypothesis is that this might actually be the most sensitive type of laboratory beta gamma coincidence system. And some measurements have been done by Lee et al. That was published earlier this year in NIME, and we're hoping to conduct similar measurements using the plastic scintillator detectors from Sauna and also from Xenon International, set up in a high resolution gamma detector system. So conclusions on future work. We've optimized our detector geometry to improve our detection efficiency by enclosing the PIPS box in 2 large high-purity germanium detectors. We are using high-resolution beta-gamma coincidence spectrometry to improve our sensitivities to metastable isotopes, 131M and 133M, and particularly in a high background of Xenon 133, compared to our current system using sodium iodide and plastic. A high-resolution gamma-ray detector means it's possible to resolve the cesium and xenon X-rays and create separate projections, and the signals from the K-alpha and K-beta can be used selectively and then summed afterwards. The PIPS box geometry is actually excellent for getting a near 4-pi geometry. It means you can get your germanium detectors extremely close together. But more work is required to determine whether the drop-off in detection efficiency is worth the enhanced electron energy resolution. So hence we're testing a plastic and germanium system with measurement and simulations at the moment. Just a quick thank you to some others that have contributed to this work, and we have a corresponding poster on some measurements that we've done with this type of system. And I'd encourage you to go and take a look at that, and also I'd be happy to answer any questions. Thank you.
Thank you, Matt. Great presentation. Really interesting to see that resolution is not always everything, and good to see that you're planning to continue exploring different options. We have a question here. Will the high-resolution laboratory system have significant practical advantages in cases where activation xenon may be observed? Could it aid in the discriminations, in the specificity, as well as the sensitivity?
Well, I think the answer is yes. When you look at the isotopes that you get from activations, Xenon 125, 127, 129M, I think colleagues from PNNL have talked about some of these isotopes earlier. I don't have the decay schemes in front of me, but I'm sure that some of the coincidences that you see from those types of decays show up in much greater resolution in these types of systems. However, it should be caveated that obviously you do have a drop-off in detection efficiency, so it would always be difficult to say whether you would actually improve your sensitivity to them.
And only future will tell how much we need to detect them. Okay, so we can maybe go now. Let's but we had some questions in the chat from Michael, but we can maybe come back to that later. There might be also more questions to your presentation. So we can move on to the next presentation at this point. We're making good time, actually. So Sergei Pachomov, excuse if I'm not pronouncing it correctly, there's a presentation on Argon 37. And I believe let us run from here. And Sergei is muted.
Hello.
Yes, we can hear you now.
Okay, can I to begin?
Yes, please.
Thank you. My name is Sergei Pakhomov. I represent Chlopen Radium Institute, St. Petersburg, Russian Federation. The theme of my presentation is installation for the measurement of low activities of Argon 37 based on the detection of liquid argon scintillations. Next slide, please. Why are Argon 37 measurement important? One of the key evidence of a violation of CTBTO is the detection in the subsoil air elevated concentration of the Argon 37, which is formed in large quantities in interaction of neutrons with the soil calcium. The concentration of Argon 37 retains high value for much longer time than Xenon radionuclides, so it is the ideal witness of underground nuclear test. Therefore, the Argon 37 is a relevant radionuclide for the CTBTO on-site inspection division. Also, Argon 37 is generated in the atmosphere under the influence of neutrons, and therefore can be an indicator of a large neutron fluence into the atmosphere. Therefore, Argon 37 can also present the interest for the international monitoring system. The development of a new equipment and methods for the measurement at the background level of various media is very urgent. Since the 2080, the Radium Institute, under the contract with the CTBTO, develops a prototype of a new kind installation for measuring activity of Argon 37, based on the registration of its own scintillation of liquid argon. Next slide, please. Two underground laboratories are capable to measure Argon 37, one Swiss and one American. In addition to mobile system, one Chinese and one American, but with high MDC of 25, 35, and 7 to 10 millibecquerels per cubic meter of air, respectively, are available to date. Pictures 1 to 3 shows some of these installations. Next slide, please. The capacity of proportional gas counter does not descend several liters and cannot be significantly increased. Due to the high argon content in the atmosphere, the volume of equivalent air sample also cannot be significantly increased, which limits the sensitivity of measurements. One of the possible ways to increasing the sample volume is to convert argon to liquid state. Due to the good scintillation properties of the liquefied noble gases, including argon, principally it is possible to measure the activity of argon 37 in the sample by registering the scintillation of the liquid argon itself. However, on the way to implement this method, it is necessary to solve a number of problems. Next slide. Problems. At normal atmospheric pressure, the melting and boiling points of argon differs only by 3.5 degrees. This range is difficult to control. The wavelength of the light emitted is in the far vacuum ultraviolet, and its direct detection requires special PMT. Impurities, especially oxygen, significantly impair the light yield of argon scintillations. Energy of Auger electrons of argon 37 is small. Number of emitted photons is also small. Decisions. Increasing the pressure by 1.5 bar, the melting and boiling points expands to 12 degrees, which simplifies temperature control. The use of wavelength shift tetraphenylbutadiene makes it possible to use conventional PMT. When testing the prototype, we used pure argon grade 6.0. The registration system needs to be highly efficient. Next slide. To the problem of small number of photons. At the electron energy of 1 mega electron volt, the light yield of liquid argon is not less than of sodium iodide and amounts to 40 photons per keV. Approximately 25% of photons are emitted in less than 10 nanoseconds, fast component, the rest in 1.5 milliseconds, slow component. The yield of the slow component is greatly reduced due to ionizing quenching at low electron energies, and according to literary sources at 12 keV, it consists only 19 photons per keV. For an electron energy of 2.8 keV, the light yield can be estimated by the Birk's formula by the value of 30.5 photons per keV, as shown on figure 5. Total photon output for argon 37 is about 40 photons per decay, 10 fast and 30 slow component. Taking into account the quantum PMT efficiency of 20%, 8 photoelectrons remain. Therefore, the efficiency of light collections should be close to ideal. Next slide. The block diagram of the setup for registration liquid argon scintillation is shown on figure 6. Prepared gases contained in cylinders mounted on the ramp. These cylinders contain high purity argon, pure argon with addition of argon 37 and with addition of some portion of xenon. Using a dosing gas system, the gas under the small excessive pressure, about 1.5 bar, enters to detecting unit where it is liquefied in a 100 cubic centimeter measuring chamber. The required temperature controlled using a system of sensors and maintaining using a cryogenic pump and heater under control of special temperature controller. Signals from the detecting unit are processed by Cayenne Digitizer DT 5790 type with 250 mega samples per second, 12-bit waveform analyzer. Next slide. Currently, the installation is assembled and operational. Its general view are shown on figure 7. During the adjustment process, a number of shortcomings were identified regarding insufficient tightness and light insulation of the measuring chamber and shortcomings in the operation of the cryogenic cooling system, which have already been eliminated. At present, the detecting unit is being fine-tuned to ensure the required quality of light collection and to increase the detection efficiency. Next slide. In this figures, detecting unit in active shield, thermal, and lead shield sectional view of the detecting unit and detecting unit assembly shown. Next slide. In this figures, this figures shows Wattman liners and the plexiglass window covered with tetraphenylbutadiene, measuring chamber assembly and installing the measuring chamber into the detecting unit. Next slide. To test the light collection, we used a small-sized tritium source in a liquid scintillator, which was located in the lower and upper parts of the measuring chamber. In figure 15 shows spectrum recorded by measuring, in figure 14 showing spectrum recorded in the different tritium source position. It can be seen that the signals are attenuated by factor 2.5, which indicates insufficient light collection. In figure 15 shows spectrum recorded by measuring ferrum 55 source in argon gas. The result indicates insufficient light collection. Registration efficiency is only 3%. Next slide, please. To adjust the parameters of the digitizer, we used measurements of the alpha source of plutonium 238 in gaseous argon. Figure 16 shows the waveform of histogram recorded by Digitizer. In figure 17 shows the spectrum recorded when measuring the alpha source of plutonium in argon gas. Efficiency testing by measuring plutonium alpha source in argon was about 43%, which testifies to the correctness of the setting of the measuring tract. Next slide, please. Based on the above, we can conclude that the mechanical, gas, and cryogenic parts of the installation for registration liquid argon scintillation are completely ready and operational. The electronic measuring tract is functional and configured correctly. The efficiency of light collection is still insufficient to achieve the required value of the detecting efficiency of argon-37 scintillation. The tetraphenylbutadiene coating and the base for its application also needs to be optimized. The use of the tetraflex base or analog doubles the collection of light. To increase the light collection, it is advisable to make a light guide from a transparent and low thermal conductivity material, plexiglass as an option. The purity of argon after manipulation of adding argon-37 probably does not meet the requirement of grade 6.0. It is advisable to consider the possibility of using a laboratory post-treatment system. Thank you very much for your attention.
Thank you very much. Very interesting presentation. Okay, at this point, there's no question, but we have a few minutes time that may allow us to go back to one of the earlier questions. Okay, so a question for Mike. Regarding the single PMT, will it add more noise into the system compared to the multiple PMTs because you're losing the coincidence?
I don't think it will overall. It might be a little bit, but we generally improve on resolution as well by having the single PMT. And so when we've looked at compared to like Xenon International or some other, looking at that for their single PMT detectors, they have, I think, an improvement in the MDA is still as well. And so there shouldn't be any detrimental effect to going to the single PMT.
It's good to hear. Okay. So, Sergey, Argon-37 is one of the most challenging radiometric measurements ever made. Congratulations to you and your team for a truly heroic piece of work, and good luck with the light collection upgrades. So, obviously, a comment more than a question. How long do you think you will need to complete the upgrade of the light collection? Oh, sorry, I'm muted. Oh, back to muted. Sorry, just wait a second. I think we'll need to unmute you. Okay, now it's gone again. Okay, we'll try one more time, maybe. We still can't hear you, sorry. Can we?
Okay?
Okay, now we can hear you. Thank you. Thank you.
Please repeat your question because technical problem.
Yes, yes. How long do you think you will need to improve the light collection?
I see two grades of this problem: short grade and long grade. Short grade is to improve light collection with light guide from plexiglass. And this work now on going. And long decision is to maybe to try some various more optimal configuration of measurement chamber and PMT. Because firstly, when we began this work, we plan to use special low temperature PMT of Hamamatsu specified for neutrino and dark matter experiments. But they was unavailable for us, and Hamamatsu R3031 was chosen as an alternative. And because its photocathode cannot be cooled below minus 80 degrees, which requires complicate the design in the measuring chamber. And it's one of the one of the grade of low photo collection efficiency. It's not very it's not simple problem.
Definitely it's not. So will the 8 photons that are collected, are they impacted by the TBB and reflector efficiency?
Reflector efficiency. I think Tetraflex can help us to improve the reflecting properties of material of chamber. Because Wattman is not enough good, and Tetraplast not covered by tetraphenyl butadiene, and it's not many material can be used in this case.
Yes, so
It's thank you.
it's certainly a difficult environment.
So there's one more question from Matt.
Okay. So we have one more question from Matt. Your talk was too good. There aren't that many questions.
I had a question for Michael, if that's okay. I wondered, Michael, how the binary gas pressure sensor that you use compares to a GC. Do you see any differences in accuracy or anything like that? And anything of note?
See good accuracy. I think the main thing is the GC. You have kind of the full gamut you can do with it at one point in time. With the binary gas one, you have to do the pre-calibrations to say, oh, I want to compare the xenon with the nitrogen, or xenon with helium, or xenon with air. You have to have those kind of pre-calibrated so you know what the sensor reading actually means. And so it requires that initial investment, I guess, to be able to utilize it to a sufficient degree.
Sure. Thank you.
Okay, one more question. The system probably needs preparation for a subsoil air sample to be measured to extract the argon. Do you also work on this process, or are you only working on the laboratory system? And how long would the sample preparation take?
Excuse me, it's a question for me.
Yes, yes.
The question is if you're only working on the gas measurement system or also on the gas processing part of the system. How to get the argon? Is that part is that part investigated by you as well?
If I understand question, excuse me, I not very good understand.
It's okay. Your presentation was mostly about the laboratory system, not about the preparing air sample, soil air sample for.
This aspect of problem was not considered about processing and sampling of argon. The aim of this installation is principal demonstration of possibility to measuring argon 37 and in the case of success, this installation can be used to measure the samples of industrial argon manufactured in nearest gas factories, and it's some kind of monitoring can be organized in such way. I think so.
Yes, makes sense. I think we have to close this session. I would like to thank again the speakers and the audience for their participation. Very interesting, and please continue the discussion in the forum, in the chat mode. You can contact the speakers directly. Please make use of all the available communication. Thank you very much, and please enjoy the rest of SMT.
Mm-hmm.